Today we continue discussion of Rusienaarrs-Schneider model. I will recall some facts, and then we continue and construct some solutions, and then we also discuss its relation to Knižnik-Zamolodchikov equations. And finally, if we have time, we also discuss some open problems related to quantum classical duality. So we are discussing trigonometric Rusienaarrs-Schneider model at quantum level. And it is given by Hamiltonians where Sk are the following operators. We wrote them last time, but let us do it again. S plus minus k is equal to sum over all possible subsets of indices. So we have n particles, and the sum goes over all subsets of degree k, where k is this number. And here we have a product over a pair of indices where one belongs to this subset and another do not belong. H plus minus qi minus qj. Then a product of shift operators. And finally, again, a product of these functions h, qj minus qi. And again, I belongs to the subset and j do not belongs to the subset. And these h plus minus functions, h plus minus functions, are some explicit functions. In trigonometric case, these are the following functions: qi minus qj plus minus I nu, where this I is the square root of minus 1, divided by sine over 2L qi minus qj, and all this in the power 1/2. The shift operator acts by just exponent of the differentiation with respect to qk. Probably it will be good to write down the first one, Hamiltonian. Just a second. Maybe I have it here. So just to just for example, we last time we also discussed briefly classical analog of this model, and its limit to Calogero-Moser system. Just let me write here the classical analog of these operators, since it's just to illustrate that it is not so awful as you may imagine from this huge formula. So in fact it is just a product over I, where I is not equal to j, square root of 1 minus multiplied by exponent of momenta. So in fact, this is a Hamiltonian of Rusienaarrs-Schneider model. And if you put also S minus, then you will get minus here, and they sum up to cosine. So then the dependence on momenta will be not like exponent, but cosine. So this is the simplest example, and we are looking to these operators. One can show that they indeed commute with each other. Not only these operators, but all these operators commute with each other. S plus minus k, S plus minus m commute. It is not easy task to show it, but it can be done. And in fact, originally in the original paper by Rusienaarrs, in his first paper on this topic, he showed commutativity of these operators. He deduced some identities for this functions h, and showed that, for example, this formula provides solution to those identities. Now let us follow our recipe. Our recipe, which we discussed for the Calogero-Moser model, was to conjugate these operators in such a way that the conjugated operator has some special sort of eigenfunctions, namely symmetric polynomials. And it can be also performed here, but in a slightly more complicated way, but the idea is very similar. For this reason, we maybe not like this, but like this. For this reason, we would like to rewrite these operators in terms of new variables, and these variables are, let us put it also here, this Q large, where Q large are exponents of Q small. Then we may write these operators as k. Let us write S plus k in terms of these Q large. And then we have, so maybe I should write here. First of all, we have this formula for the functions h as functions of Q large, t plus minus 1 qi minus qj divided by qi minus qj, all this square root, and this t is equal to exponent of minus nu divided by L. So using this formula, we substitute it here, and we also substitute the shift operator. The shift operator in these coordinates, the shift operator just multiplies the corresponding q, so it let us write it also t plus minus k acting on some function of q large multiplies the q kth coordinate by q small in plus minus power. So the shift operator, the action of the shift operator is defined. The set of functions is also defined. And we may write now just the same formula, but in new coordinates. This is also the sum over j, where this j has degree k. And just the same thing. And here we have t qi minus qj divided by qi minus qj. Then we have a set of shift operators, TL plus, where L belongs to J. And finally, we have again a product of these functions H, which are in fact written as given here. So it's been written in these coordinates, in this form. It is a little more clear what kind of structure do we have. In this operator. And now we're going to conjugate it with some function which is in fact a ground state. So our idea when we considered Calogero-Moser model was to conjugate initial quantum Hamiltonian with some function which is in fact a ground state. And after conjugation we obtain an operator which has symmetric polynomials as eigenfunctions. And the same we are going to do now. For this purpose, you may also, for example, move these shift operators to the right. If you do it, then you see you obtain this I belongs to J, and this index I belongs to J, and the shift operators acts towards the indices which belongs to this subset J. So after you move this product of shift operators to the right, you will obtain here also Q. If you move this product to the right. And then the conjugation is as follows. You should conjugate.
After moving, there's multiplication by Q. What does it mean? Small Q.
If you so you have a function of Q here, of coordinates here, and you have a shift operators here. So these are difference operators, and these are functions. So if you move these difference operators to the right, then these q's will be multiplied by q. Yes, just because this index I exactly belongs to this subset J, and this J small doesn't belong to this J large. This is why they are not shifted. These coordinates are not shifted, but these are shifted. So this ground state, which we are going to use, ground state, is more complicated than in the Calogero case. It has the form. Let me write it first like this. It is a product. It is also van der Monde kind formula, but it has infinite number of factors. Qi minus Qk Qj, Qi minus T Qk Qj. So there is an infinite product here, yes, and we may let us rewrite it in the following form. We write it like a product, an infinite product of delta k, where delta k is just a van der Monde type product of I'm sorry, all this should be also in the 1/2 power. And this Qi minus Qk Qj minus divided by Qi minus T Qk Qj. This is it. And I won't go into details of this conjugation, but if you do it, you may perform conjugation step by step. Just you have a product. This our delta, our ground state, is a product of delta 0, delta 1, delta 2, and so on. And you may perform conjugation step by step. Just first conjugate it by delta 0, then conjugate by delta 1, and so on. And if you do it, you will see that each time you obtain some consolation. So this is what we're looking for. And I'm just saying that you may first do conjugation by sigma 0, then what you obtain is you should also conjugate by sigma 1, delta 1, I'm sorry, and so on. And each time some terms will cancel out. So if you have you see, you'll have some ratios of rational functions of q's with square roots, of course. And each time you will have some consolations. And finally, we obtain the following operator. So I won't go into details because it's just much more easy to do it by yourself than to write on the blackboard. The final answer is what is known as McDonald operators. In fact, it is obtained up to some constant, but it doesn't matter. So we have again a sum over all subsets of degree k, and here we have a product of tqi minus qj divided by qi minus qj and multiplied by the product of shift operators. So after conjugation, you see these operators become much more simple. They take much more simple form. So in fact, up to this factor, this is what is called McDonald operators. And this is another way how to prove commutativity of initial operators. You may think about it. If you have read the book by McDonald and you know that these operators commute, then turning back, you may, of course, obtain commutativity of the initial operators Sk. And what is important for us is the property of McDonald operators that they have eigenfunctions given by symmetric polynomials. This is a very important property. We just formulate it. Maybe I will show you some simple example. But we just formulate it by words. With reference to book by McDonald, that you may define a set of polynomials, of symmetric polynomials, which depend on the coordinates of particles and on this pair of parameters. So we have two parameters here, yes. This t, which stands here, and this encodes the relativistic parameter. When it goes to 0, this t goes to 1. This, together with some rescaling of shift operators, all this goes to Calogero-Moser Hamiltonians. And this q is a parameter of the shift operator. So we have two parameters, and we again may use symmetric monomials, which we previously used, in fact. And so these polynomials are represented again in the same way, but this is just a general form. This is just a statement that the polynomial begins with some monomial function, symmetric monomial function, which we defined previously, and it has some tail, some additional terms with this partial order. And there is a scalar product on the space of these polynomials. Let me write it also. The so-called whole scalar product. This is some factorial, some combinatorial factor here, delta lambda mu. The product, this is the length of the Young diagram. And these are parameters of a partition. We have some partition which defines this symmetric polynomial. And so this is a scalar product. Maybe I have here. I'm not sure if I have here a formula for z, but if not, Yes, I have it. That lambda is equal to 1 m1 m1 factorial 2 power to m2 m2 factorial and so on, where these mi are multiplicities of parts of lambda I entering the partition. So in fact, you may find all these formulae in the literature, in the original papers, and you may look to the book by Gleb Arutyunov and find explicit formulas there. And this, let me recall that this M, the symmetric monomial, is just a sum over all elements of symmetric group. Q1, Q sigma of 1 to the power of lambda 1, and so on. So these are symmetric monomials, and we use this basis, and in this basis, McDonald polynomials are somehow represented. And the statement is the following, that these McDonald polynomials are eigenfunctions. Let us write it like, so in fact these are McDonald polynomials without this vector, so maybe I should put a prime here. And if I'm not mistaken, the original McDonald polynomials without this factor has these symmetric polynomials as eigenfunctions with the following eigenvalue. This hk is equal to the sum of j1 minus, or j1 less than, and so on up to jk, q to the power of j lambda j, t in the power of n minus j. So let us perform some simple examples. For example, let us. So
you say this is the McDonald polynomial?
no, McDonald operator. McDonald operator and McDonald polynomials are eigenfunctions of McDonald operators. This is McDonald operator without this factor. And McDonald polynomials defined here are eigenfunctions of these McDonald operators with these eigenvalues.
In which space is this operator? From which space to which space is this operator acting?
This operator acts on the space of symmetric polynomials.
Okay. So they're just symmetric. There is no additional condition, like add invariant or something like that.
This no. Of course, you may. So you may try to find it step by step. Likewise, we did it in the case of Kalodger-Moser model. But so the final answer is formulated as follows: that if you are looking for polynomial solutions to eigenvalue problem, then these polynomials are represented in this way, and they can be this is a very general form, in fact, because these coefficients are not defined. but just to, in some way, these coefficients are fixed if you fix also some scalar product on the space of these polynomials. And this is just the answer for this scalar product. But it is also not a direct way, just I cannot give you a general formula for these coefficients. But I can show you some examples, some simple examples. Let us consider an empty Young diagram, first example. Empty lambda, empty partition. What does it mean? Empty partition means that this polynomial is equal to 1. It is independent of coordinates. And we think about it as, what should we verify in this case? In this case, you see, yes, and let us also, for example, this is example. Let us also think that we have only two particles, just for simplicity. Then what we have? So let us write this operator. Maybe it's better to write this one. mk prime is equal m1 prime. So k is equal to 1. And what is this operator? It is tq1. So let me write the answer and then I explain. tq1 minus q1 minus q2, t1 plus tq2 minus q1 over q2 minus q1 t2. So this is the first operator when k is equal to 1 and n is equal to 2. So we have two particles. Then we have only a single non-trivial operator, which is given here, just because you see when the sum goes over all subsets of length 1, so it means that the sum goes over ordinary index, and this index runs over all possible values from 1 to n, so from 1 to 2 in this case. When I is equal to 1, then we have this product. I is equal to 1, you see, 1, 1, as given here. And j is not equal to 1, it equals to 2. J is equals to 2. And this is T1, is a shift operator along this Q1. And the same for the second term. So when I is equal to 2, then we have a shift operator T2, and this I is equals to 2, so we have Q2 here and minus Q1. So this is a simplest McDonald operator, and let us look at its solutions and its eigenvalues. So let us verify the eigenvalue. For example, what we have here when empty, what means empty diagram? It means that lambda 1 and lambda 2 is equal to 0. Then what do we have here? This eigenvalue h1 is equal to q is cancelled out because it is in the power which is equal to 0, and we have only t plus 1. Yes, because we have this index j. Let me write it. I'm sorry, I just put here a lot of indices, but I should put only J. So when J is equal to from 1 to n. So when J is equal to n, we have 1, and when J is equal to 1, we have t. This is the eigenvalue. And let us verify it. So how to verify? The action of these shift operators on 1 is by definition 1. So we think on that T1 acts on 1 by 1. There is nothing to shift. And T2 acts on 1 by 1 also. With these definitions, we have the action of M1 prime on our symmetric polynomial given by 1. We obtain just a sum of these coefficients, yes? This plus this. T Q1 minus Q2. And let me write it like minus T Q2 minus Q1 divided by Q1 minus Q2. I changed the sign. We have here Q2 minus Q1, but I put here Q1 minus Q2. So we see that we obtain T Q1 minus Q2 plus Q1 minus Q2 divided by Q1 minus Q2. And this is T plus 1. This T plus 1 is this H1. The second example, let us consider the first non-trivial example when we have a unit diagram given by one box. One box means that we have lambda 1 is equal to 1 partition and lambda 2 is equal to 0. In this case, we have what? Just a second. In this case, we have this H1 equal to TQ plus 1. Yes, because when lambda 1 is equal to 1, this gives you Q. And at the same time, when J is equal to 1, we have also T. And when J is equal to 2, then Q to the power of 0 and T to the power of 0, 2. So we have this eigenvalue, and we can verify it. This is eigenvalue corresponding to symmetric monomial functions with this partition. How it looks like. We have this m lambda, which is equal, in fact, to Q1 to the power of lambda 1, Q2 to the power of lambda 2, and plus symmetrization. And in this case, there are no diagrams less than this one, so there is no tail. And this provides us just a Q1 plus Q2. And this is our McDonald polynomial. So in this case, in this simple case, the McDonald polynomial is given just by the sum of coordinates. And we may also verify it. So let us write it here. We have this polynomial now, the action of T1 on this polynomial. How it acts? It multiplies this Q1 by Q small, yes? Similarly, the action of T2 on this polynomial is given by Q1 plus Q2 multiplied by Q small. Okay? Now we act by M1, by this operator, by M1 prime, to this polynomial, and what we obtain. Let us write explicitly. So we have this coefficient, T Q1 minus Q2, Q1 minus Q2, multiplied by T1 acting on P. So by Q small Q1 plus Q2, and then plus this coefficient multiplied by this expression. And now let us have a look at first. So we should simplify this expression. Let us have a look at all terms corresponding to the first power of Q small. What we have? We have here T Q1 minus Q2, Q1 minus Q2 multiplied by Q1, yes, plus this T Q2 minus Q1, Q2 minus Q1 multiplied by Q2. This is correct. So let me change the sign here and change the indices here at the same time. So what we see? Then we see that these terms are cancelled out.
So, what is this small q? T1 act on P is Q1 plus Q2. What is this Q?
This Q? Yes, this comes from this shift operator, shift operator.
Shift by Q?
Yes, it just multiplies the corresponding coordinate by Q small.
So we can change the order. Q2 times small q is equal to Q times Q2.
Sorry?
So this is the...
So if you have any function of this, of Q1 and Q2, the action of T1 is equal to f Q small of Q1, Q2. This is just the action of shift operator. And similarly for, if you have T2, then this Q goes to this argument, yes? So I want T2 on f of Q1, Q2 is equal of. So this is a definition of shift operator. Now what we see here that these terms are cancelled out, and these terms we have T Q1 squared minus Q2 squared divided by Q1 minus Q2. So it is T multiplied by Q1 plus Q2. And now let us look at the order Q0. In the order Q0, we multiply this coefficient T Q1 minus Q2, Q1 minus Q2 multiplied by Q2 minus, I put minus and change the sign here, T Q2 minus Q1 multiplied by Q1. And this time, these terms are cancelled out. And we are left with the just with Q1 squared minus Q2 squared divided by Q1 minus Q2. So it is Q1 plus Q2. So finally, I want to say that finally our M1 prime acts on this Q1 plus Q2 provides us first, this was coefficient behind Q. So we have QT Q1 plus Q2 plus Q1 plus Q2. So what we have is just TQ plus 1, Q1 plus Q2, and this is a eigenvalue as was predicted by general formula, but this is of course very simple illustration, but however you may do it by yourself in more complicated cases. Okay, now so we discussed the general structure. Yes, and you may of course now come back to initial operators because now we know that these operators M prime has eigen polynomials, and these polynomials are McDonald symmetric polynomials. And then you may also remove this prime, multiply it by that factor, t to the power of some n by k by n minus k 1/2, and also perform inverse conjugation, and then you obtain the solution to initial problem. And the solution to initial problem will be given by this ground state multiplied by symmetric polynomial. So this is a just general recipe how to construct solutions to eigenvalue problem. And now I would like to discuss the relation of this model to Knižnik-Zamolodchikov equations, because it is also important for us to understand this relation in the following sense, because we use very different approaches for studying many body systems on one hand and spin chains on another hand. Here we studied quantum many body systems and described a set of solutions generated by symmetric polynomials and so on. And when we discussed spin chains, we used algebraic beta-ansatz method. And what I want to say that these models can be related, and they can be related. I mean, the models of type of spin chains and the models of many body systems type. They can be related through Knižnik-Zamolodchikov equations. And let me explain how it can be performed. For this purpose, I need to recall some facts, but I will do it briefly. But however, I need some concrete formulas to be written. First of all, let me recall the formula for Hamiltonians of spin chain. Generalized spin chain. In this case, we had the quantum transfer matrix, which was a trace of a product of R matrices. Maybe we should put inverse order. So we have this definition. This was just definition of a transfer matrix, and I just recall you that the transfer matrices commute with each other at different values of spectral parameters, and this follows from RTT relations. So this is a generating function of quantum Hamiltonians, quantum commuting Hamiltonians. Yes, and we also put here the twist matrix. The twist matrix was also here. Just let me put it, this twist matrix. So, in the concrete case, when R matrix is of the following form, R12 of x is equal to 1 plus eta divided by x p12, in this rational case, with this Young's R matrix, we obtain the following expression. So this is a product, and this product, of course, can be represented in the form of the sum, just because here we have a product of factors, and each factor has a simple pole at some point with respect to the variable z. It has some pole here at point zn, zn minus 1, and so on. And we may decompose the product into a sum, and these coefficients can be computed. And we did it previously, and I just write you the answer. The answer was as follows. It was Ri, yes, like this. And each R matrix here depends, in fact, on the difference of corresponding spectral parameters. So, for example, I1 depends on Zi minus Z1, and so on. Ji, and here Rin up to Ri plus 1. So this was a formula for the Hamiltonians of the spin chain, on one hand. On the other hand, we discussed also, this is a spin chain, data corresponding to spin chain, and now we would like to compare them with Q-Kazet equations. We also discussed the quantum Knyzhnik-Zamolodchikov equations. These were equations of the following form. We have, in fact, this Ti, the shift operators, defined in our terms like this. And here we have some operators. And the form of these operators is very similar to the form of these Hamiltonians, but not exactly. Let me write it here. This form is similar, but the R matrices, the first product of R matrices have R matrices with shifted arguments. So we have here Ri I minus 1, but depending now on not on only difference of parameters, but also on additional shift. And then the rest of the formula is just the same, is just very similar, but again not exactly. So let me write it, and then I explain what I mean. So you see what is the difference between this set of operators and this set of operators. In the first product of our matrices, which is before the twist matrix, our matrices here are shifted by this e to h. And there are no such shifts here. And here we have just a product of our matrices, but here, in contrast to this formula where we have a product of inverse R matrices. In fact, if we have a unitarity condition when R1, 2 of x, R21 of minus x is equal to 1, if it is so, then we may change this. If it is so, then we could change this R matrix just by using this unitarity condition, and rewrite the last product just in exactly the same way as we have it in this expression for Hamiltonians of spin chains. But even in this case, we still have this additional shifts. But the difference is not difference is also in normalization of our matrix. You see that our matrix, which is used here, is not unitary. It doesn't satisfy this condition. It is proportional to identity operator, but there is some factor here. Just let me put it more explicitly. More explicitly, we have, in order to have this unitary R matrix, is our matrix which has the form x plus eta Pij divided by x plus eta. This is a normalization which satisfies unitarity condition. And this normalization do not satisfy unitarity condition. And for this reason, there is the following relation between these operators. Let me write it, and then I explain this result. I want to say that the quantum Hamiltonians of these spin chains Hi are equal to Ki of 0 multiplied by the product of, I also should write now maybe the same variables everywhere. So if I put now formulae together, then I should put also R matrices of X. Let me write it let me write all x's everywhere zi is identified with the xi, okay? The product over j not equal to I, xi minus xj plus eta divided by xi minus xj. This is what I want to say. This is a relation between these two operators. Again, let me explain why it happens. First of all, if we put h equal to 0, this h is a parameter entering this operator's k. If we put h equal to 0, then these shifts are absent. And we have a product of our matrices exactly the same which we have here. Then we have a twist matrix, and we also have this twist matrix over there. But we also have a product of our matrices here, and we have a product of inverse R matrices here. And so the difference between two formulas is that, in fact, we use not R matrix, not the same R matrix as in the spin chain. In the spin chain, we use R matrix which has a simple pole at 0. And when writing this Knižnik-Zamolodchikov equation, we use R matrix with tilde, which satisfies this unitarity condition. It has different normalization. This R matrix and this R matrix has different normalizations. And they are just related by simple relation. This Rij tilde is equal to x plus eta divided by x Rij. And the difference between normalizations provides this factor, this additional factor. And this factor will appear now and will give us the Rusienaarrs-Schneider model, which we just discussed a half ago. Let me show how it appears. So the way how to move from spin chain to Rusienaarrs-Schneider model consists of two steps. At first step, we lift to the level of quantum Knižnik-Zamolodchikov equations, and we fix this relation. So we have these operators in the Knižnik-Zamolodchikov equations, and we know that these operators are related to Hamiltonians of spin chains in this way. Now, the next thing we are going to do is to perform a reduction. More precisely, not a reduction, but projection. Projection of Matsov-Cherednik type. We have this set of equations. What we are going to do? We are going to multiply all these equations with some symmetric dual vector, and this dual vector. So we again fix a sector in our Gilbert space. Our Gilbert space is some vector space. This is a number of sites, and this is just some space where the structure group acts. And now, so this is a product up to n small. We have now n small particles here, and n large means rank of structure group. corresponding to spin chain. For example, we may look for GL2 spin chain. That means that n is equal to 2. And then we have just spins spins up and down. And as you, I hope, remember, in order to use Bethe-Ansatz method, we should just fix some sector in this Hilbert space and fix the number of spins up and down. So, and let us assume, and in fact this Hilbert space is decomposed to a direct sum of sectors with some fixed set of spins up and down. This is what we previously did, and I hope you may remember this. And now we fix this sector, and we choose some basis in this sector. Some basis in this sector. And then we may construct a symmetric dual vector just by symmetrizing all basis covectors. It means that any permutation operator acts by identity on this symmetric covector. So it's by construction, it's just a vector, special vector, which is obtained by all possible symmetrizations. So you just choose, you just fix, for example, you have a configuration corresponding to spin chain where some, for example, two sides you are looking to configuration where two sides are with spins up and the rest with spins down. When you just fix it, and then you may write down some basis element in this space, and you just symmetrize over all possible permutations. So the latter means that by definition, any permutation operator acts on this covector, on this special covector by 1. So we have this defining relation, and so our strategy is just to consider this set of expressions and sum up them over all possible values of index. This is what we are going to do. Okay, now what we should do, you see that this permutation operator acts by 1 on this omega, and the latter means that if you act on this omega by this r tilde, we obtain, you see, x plus eta pi ij divided by x plus eta. This pi ij acts by 1. Then the action of this R matrix is also by 1. Yes, because you just substitute 1 instead of this permutation operator. But and what we do, we multiply both sides of this equation by this omega. We have shifted R matrices here, and we use this relation in a very tricky way. We don't write that the action of R matrix to omega of shifted R matrix. Let me denote it maybe by plus. R plus, meaning that R plus, this plus is a shift, is additional shift of this argument. But we treat this relation in a different way. We write it like this. We write that you may substitute not shifted R matrix instead of shifted. So we just don't write identity here, but we write the same R matrix, but which is not shifted. And if you do it, then you will see, then you will see that when you compute this expression, it is the same as to compute expression ki of 0 psi. And ki of 0 psi is just a product of this xi minus xj plus eta xi minus xj. Like this. And after summing up all these equations, you will obtain the sum of Hamiltonians of quantum spin chain. In fact, you should write, it's a more accurate statement is as follows. Let me write just, I won't go into details because I don't have time, but let me just formulate some result. The result is as follows. If you consider, let us consider this function psi. Then the action of the following operator on this psi, and you may recognize the rational analog of McDonald polynomial, and this is in fact the rational Rusienaarrs-Schneider model. So this is the Rusienaarrs-Schneider Hamiltonian, which is not trigonometric but rational. It's very similar to what we just discussed. And then if you sum up all these equations, then you obtain the following thing. You obtain omega sum of h psi. And this sum of h can be also computed. The sum of h is just a sum of all residues of the transfer matrix. And this is why it can be shown that this that the sum is in fact equal to the sum from 1 to n of ji. This is just a theorem for residues. Then the sum of residues at finite points should be equal to the residue for the expression at infinite point with inverse sign. And so you may compute it and show that it is that it can be represented in this form, and this allows to compute the final answer. That the final answer will be e to psi, where so this we have this Schrödinger equation where this eigenvalue is is the following expression. This ji just components of the twist matrix, and these are multiplicities. So, for example, if we in n equal 2 case, we have this G equal to G1, G2. And M1, M2 is the number of spins up, and spins down. So these are quantum numbers, M1 and M2, and again, G1 and G2 are components of the twist matrix, and they form this spectrum of this problem. And in this way, we may relate spin chains and quantum Knižných-Zamolodchikov equations to quantum many-body systems. So this, the main idea is that there is a projection, there is a strong projection which maps solutions of spin chains type or Knižných-Zamolodchikov type, which belongs to this large space. But if you choose some special direction in this space, special direction generated by some kind of symmetric covector of this type, then the projection to this direction gives you solution to quantum many-body system. And this quantum many-body system is a many-body system of Calogero or Rusienaarrs type. And this is what we what I tried to show you. And there is also a very interesting continuation of this topic related to some open problems, because you may now consider a limit when h go to 0 everywhere here. And in this case, as we know, in this case, we obtain just exactly spin chain. We don't have Knižných-Zamolodchikov equations anymore, but we have only spin chain on one hand. But on the other hand, if we look at this model, we see that this h is just a Planck constant. So if we consider in this limit, we obtain relation between quantum spin chain and classical many-body system of Rusienaarrs or Calogero type. Many-body problem, many-body system. And it appears that this relativistic parameter here, so eta in this spin chain, so we consider h goes to 0, but we have eta. And this eta enters the R matrix of the spin chain, and here it is just a relativistic parameter. Now, you see that the inhomogeneity parameters, the parameters which were entering R matrices and the products in the monodromy matrix, these xi are positions of particles. Positions of particles. And in fact, generalized velocities will be equal to eigenvalues of quantum Hamiltonians. Eigenvalues of quantum Hamiltonians of quantum spin chains are equal to classical velocities of integrable many-body systems. And this is this is called the quantum classical duality, this relation. Quantum classical duality. And it is interesting by many reasons. For example, one reason you may naively think in the following way. I don't need beta ansatz anymore. Instead of trying to solve spin chain by beta ansatz, instead I may consider a classical many-body system and formulate my task in the following way. I fix one Lagrangian manifold which corresponds to fixation of positions of particles, and another Lagrangian manifold is in fact a fixation of some levels of action variables. And the level of action variables should be chosen according to this rule. So you should choose level of action variables to be equal to G1 M1 times and to G2 M2 times. And then you fix two Lagrangian manifolds and just trying to find velocities of classical particles. And what you know is that the velocities of classical particles are equal to eigenvalues of quantum Hamiltonians. And this is quite an interesting problem. It appears that you may solve it, but you have a lot of solutions in this case. And the reason for this phenomenon is that, in fact, you may one many-body system corresponds not to a single quantum spin chain, but to a set of quantum spin chains which are obtained from this one by supersymmetrization. So, and when you find a velocity of a particle, you don't know to which spin chain Hamiltonian it describes, because the correspondence relates a set of spin chains with a single many-body system. And there is a combinatorial problem just to find the rule for proper relation.
The choice of spin chain on this side.
Yes, I mean, we may write here a set of algebraic equations to determine velocity of classical particle, and we know that the solution to this equation is some eigenvalue of some Hamiltonian of quantum spin chain, but we don't know which one spin chain it is. So we have a set of spin chains, and to find the rule which relates one with another, one set with another, is I think a good problem to be solved, and it is an open problem. I don't know solution. And of course, there is another problem. Is this relation, this quantum classical duality relates is a statement about spectrum only. So it says that the spectrum of quantum spin chains are related to velocities of classical particles, but there is no statement about eigenvectors. So there is no statement about beta vector to solution to quantum problem on the side of quantum spin chain. And if one can formulate it, I think this will be very interesting. So this is an open, promising problem, and if someone is interested in this, I am ready, and I will be glad to discuss this topic. So there are a lot of open problems here. I just didn't tell you about many other relations called spectral dualities, or there are different titles for these dualities. GLN duality also. So many other interesting phenomena are related to all these structures. And so if you are interested, I'm ready, and I'll be glad to answer your questions. And we finish here.